Hi! As what I have promised, if you watch my former video with regards to overview of thermodynamics, I will be having a content which focuses mainly on laws of thermodynamics. So here's the content that I promised. Let's start! Our two main learning objectives for today is first, understand the laws of thermodynamics, our main topic for today. And then further, apply the thermodynamic concept and principles, which includes the law, in analyzing and solving problems. So let's start with the first law. We have here the Zeroth Law of thermodynamics. So traditionally, this is a bit of trivia. Traditionally, we have three fundamental laws for thermodynamics. The first law, the second law, and then the third law. But then, there is a more fundamental law or more basic law, which is later then labeled as the zeroth law. So what we have here is the zeroth law of thermodynamics. So the statement goes like this. Two bodies are in thermal equilibrium with each other if both has the same temperature reading, even if they are not in contact. Further explanation also, when a body is brought in contact with another body, which is at different temperature, heat is transferred from the body of higher temperature to a body of lower temperature. Again, I will be highlighting this. Heat is transferred from the body of higher temperature to a body of lower temperature until both attain the same temperature. Upon attaining same temperature, at this point, the heat transfer stops and the two bodies are said to have reached the thermal equilibrium. So, at the point of heat transfer, and then again, if they already have the same temperature, the heat transfer stops and said to have reached the thermal equilibrium. If you watch my first video about the overview of thermodynamics, I think I already mentioned this, but this is worth reiterating because we will be next discussing the first law of thermodynamics, which is the basis of the first law that is quite correlated with the conservation of mass and energy. So since we are talking about laws of thermodynamics here, I will be mentioning again and again the law of conversion of mass and energy, which states that the total mass is a constant. So mass is constant. This means that the total mass entering to a system is equal to the total mass leaving the said system. Again, the highlight of the conservation of mass and energy is the total mass entering to a system is equal to the total mass leaving the system. Here, I will be giving you a brief definition of the different forms of energy. We have here four. First, the potential energy labeled as P or PE. This is the energy produced due to the change in elevation. Later, I will be revealing the formulas for this for potential energy, then kinetic energy, then work, and then heat. Second, definition of kinetic energy, usually or generally labeled as Ke. This is the energy produced due to the mass and velocity. You will be seeing its formula and it is related with mass and velocity. And then third, work. Work is the product of the displacement of the body and the component of the force in the direction of the displacement. So, work again is product of the displacement of the body and the component of the force in the direction of the displacement. And lastly, we have heat, usually labeled as Q, QA, and then QR. Heat is formed due to the temperature difference. So, heat, you always hear about temperature difference. So, I will be advertising also my heat transfer video. I am actually recommending it to you if you want to know more about heat transfer. So, I hope I already give you the brief description of the different forms of energy. Later, I will be giving you the formulas related to it. So, let's proceed. So, based on experiment observations, the first law can be simply stated as during an interaction between a system and the surroundings, the amount of energy gained by the system must be equal to the amount of energy lost by the surroundings. Again, the amount of energy gained by the system must be equal to the amount of energy lost by the surrounding. So if you remember, earlier I mentioned that the first law of thermodynamics is almost the same with the conservation of mass and energy. And as you can see here, the law mentioned about system and surroundings. So next slide, I will be discussing the different kind of systems. So classification of systems, first, we have here three. So first, we have the isolated system. So this system does not exchange energy with the surroundings. Again, that's why it is termed as isolated. This system does not exchange energy with the surroundings. And then we have second, closed system. In this system, only energy can pass the boundary of the system in the form of work and heat. So in this system, energy can pass, but it can be only work and heat. Again, for closed system, only energy can pass the boundary of the system in the form of work and heat. And then for lastly, we have the open systems. Both mass and energy can pass through the boundaries of the system. So again, for the open system, both mass and energy can pass through. For the closed system, we have energy only. And then for isolated system, it does not exchange energy. So I hope the difference is clear to you. Now we have here the second law of thermodynamics. So in this law, it introduces a new property called entropy, usually denoted by capital letter S, entropy, which is an extensive property of a system. As I already mentioned also the formula for entropy in the overview of thermodynamics video, wherein it is Q over T, so heat over time. So I will be stating the second law of thermodynamics. So it goes like this. The entropy change of a closed system is equal to the heat added. So that is Q or QA because we termed QR for heat rejected. Again, the entropy change of a closed system is equal to the heat added reversibly to it, divided by the absolute temperature of the system. So meaning heat over temperature. This is where our formula from the overview of thermodynamics came from. So we mentioned that the entropy is Q over T, but the specific formula is QA over T, wherein QA is the heat added. And it is highlighted also that the temperature that we will be using is absolute temperature, or in as a unit, we refer to the absolute temperature as Kelvin. And then for the English unit, we have Rankine and because Rankine based on Fahrenheit, and then we have Kelvin, which is based on Celsius. Before we proceed to the formula part of this video, we will be stating the third law of thermodynamics. So, according to the third law of the thermodynamics, the entropy of a system in an internal equilibrium approaches a constant independent of phase as the absolute temperature tends to zero. So, in simpler terms, or in a simpler phrase or sentence, As the temperature of any system approaches the lowest possible temperature or 0 Kelvin, the entropy of the system assumes a particular or the least value when the system is in its lowest energy state. Again, as the temperature of any system approaches the lowest possible temperature, that is 0 Kelvin, the entropy of the system assumes a particular or least value. So that is when the system is in its lowest energy state. Yes, this is my favorite part, the formulas part. So, I will be providing you the different formulas for the forms of energy and then for the laws of thermodynamics specifically. So, first we have here the potential energy. The potential energy is based on the definition, this is based on height or elevation. So, we have here for the formula mgh, where m is mass of the body, and then g is acceleration due to gravity, and h is height or elevation. So we have here, if we are asked to find the change in potential energy, we have P2 minus P1, or since mass is constant and then acceleration due to gravity varies, but then it can also sometimes the difference is almost negligible. That is why our formula, we can, if there is a change in elevation, there is also a change in potential energy. So we can solve for the change in potential energy by using the formula mg times h2 minus h1. That is for the potential energy. Yes, next up, we have the kinetic energy, wherein it is also denoted as Ke, wherein by definition, it is related to mass and velocity. As you can see, the formula is 1/2 mv squared, wherein m again is mass of the body, mass of the body, and then v is equal to velocity. And then if we are asked to find the change in kinetic energy, we can use the formula 1/2 mass, since mass is constant, multiplied by the change in velocity. But then our formula is v squared. That is why the change in velocity must be v1 squared or v2 squared minus v1 squared. So it is, again, the formula for kinetic energy. Always think that kinetic energy is related to mass and velocity. So for the third kind of energy, we have the work. So work is, by definition again, is force times distance. Note that, so you have to note this. Work done by the system is positive, that is out from the system. And then work done on the system is negative, that is entering to the system. Again, work done by the system, positive. Work done on the system, negative. So last, for the energy, we have here the heat or Q. So the formula for heat is mCp delta T, wherein delta T is the change in temperature, wherein M is mass again, and then Cp is a specific heat. So specific heat varies if it is water, air, or any substance. Note that heat is positive when heat is added to the system. Again, heat is positive when heat is added to the system, or this is also called as QA. And then heat is negative when it is rejected from the system. So heat is positive when it is added to the system. Heat is negative when rejected from the system. So heat is positive when it is added to the system. Heat is negative when it is rejected from the system. So keep on repeating that. Later on, you will be remembering that. So now that we are done with the different forms of energy, formulas related to them, we will be having now the first corollary of the first law. I will be defining first the word corollary. Corollary. If it seems unfamiliar to you. So by definition, it is a proposition that follows from and is often appended to one which is already approved. Again, by definition, the corollary means a proposition that follows from something or a statement that is already approved. So this is first corollary of the first law. So this is somewhat related to our first law of thermodynamics. So in short, this is, or in simpler terms, this is a proposition which comes from our first law of thermodynamics. To be exact, this is the application of the conservation of energy to a closed system. So what I will be showing you what is, so the formula flashed here now is the application of the conservation of energy, which is, again, I mentioned earlier, that is related to the first law of the thermodynamics, to a closed system. So in a closed system, energy balance on the system based on the laws that was mentioned earlier. In energy balance on the system, initial energy plus energy in, so the energy in must be equal to the final energy plus energy out. So initial energy plus energy in is equal to final energy plus energy out. So in symbols, we have here E1, that is the initial energy, plus energy in, which is Q. And then we have here Q is heat. And then we have here E2, the final energy. And then we have the energy out, that is work. So components of the initial and final energies on the system. We have for the energy 1, we have the U. U is internal energy. So U is for internal energy. We have PE1, potential energy 1. We have KE1, kinetic energy 1. And then for E2, we have internal energy 2. And then we have potential energy 2. And then we have the kinetic energy 2. Take note that for a closed system, kinetic energy and potential energy are usually negligible. Again, KE and PE are usually negligible in a closed system. So if we neglect PE and KE by equation or by canceling them out, we have the energy. So the initial energy is equal to internal energy 1. So, and then the final energy is equal to the internal energy 2. And then our equation becomes U1, wherein this is our energy 1, plus Q is equal to U2, this is our energy 2, plus work. Again, we by transposing, we have heat as U2 minus U1 plus work. Therefore, the energy equation of a closed system is Q is equal to change in internal energy plus work. So that is our final formula for the first corollary of the first law. So take note of that for a closed system. Of course, if we have application of the conservation of energy or the first law of thermodynamics to closed system, we have here for the application to open system. So that is what we referred to as the second corollary of the first law of thermodynamics. So wherein our Q or our heat formula is change in internal energy plus change in potential energy plus change in kinetic energy plus delta PV, that is pressure volume, plus work, wherein the concept of enthalpy, we have here delta H, change in enthalpy, is equal to change in internal energy plus change in pressure volume, that is PV. And then we have here substituting delta H. We have here change in potential energy, change in kinetic energy, plus change in enthalpy, plus work is equal to our heat. So that is for the application of the conservation of energy to open systems. Note that for a typical turbine, overall change in kinetic energy is so small or almost negligible, such that it is usually neglected. And then for control stations with perfect insulation, or for stations with perfect insulation, heat may be neglected. So please take note of that. I think that is more than enough for the formulas for the laws of thermodynamics. Now we proceed to the sample problem. So the question goes like this. A tank used to determine the mechanical thermal energy equality. So a tank used to determine the mechanical thermal energy equalities or qualities contains 10 kilograms of water. 10 kilograms of water. And then the total work input is 20 joules. So 10 kilogram of water, the tank contains 10 kilogram of water. And then the total work input is 20 joules. But here we have the question. Find the change in specific and total internal energy assuming adiabatic. So first, what is adiabatic? Adiabatic means, so that is a famous term in thermodynamics, that heat is 0. So Q is 0. Thus, so since adiabatic, we are considering adiabatic here, Q is 0. Thus, for our equation, Q is equal to delta U plus WN. Q is 0. So we have delta U plus WN is equal to 0. And then, since the work is done on the system, then our given, or the work input work is done on the system, 20 joules is substituted as negative 20 joules in the equation. As you can see here, 0 is equal to negative U minus 20 joules. And then, by transposing negative 20 joules to the other side, we have delta U, or change in internal energy, is 20 joules. But then, we can also, the question is specific internal energy. So, we have to divide it by the given 10 kilograms of water. That is why our final answer for this is 2 joules per kilogram for the specific internal energy. Here is a follow-up question. If a heat leak of 0.1 joule per kilogram is noted, what is the change in internal energy? So first, note that heat is negative when rejected from the system. So the keyword here is heat leak. So Q is equal to negative 0.1 joule per kilogram. So since the heat is rejected, we have to substitute our given 0.1 as negative value multiplied by the given 10 kilogram of water. So our heat now is negative 1 joule. So as if we have here negative 1 joule as heat, substituting it to our formula earlier, which is Q is equal to delta U plus WN, wherein we have Q as negative 1 joule, the heat leak, and then we have the work input, which is negative 20 joules. From the formula, our change in internal energy is 19 joules. And then, the specific internal energy is 19 joules per 10 kilogram, or simply 1.9 joules per kilogram. So let us always, again, if we One tip, if we are taking exams, let us always take note of the exact question and also for the follow-up question, because sometimes you are about to get 5 points but then you neglect, or due to carelessness, you forgot the other question. So that's my tip for today, and I hope that you gained something from my content today. So again, if you wish to have a copy of this PowerPoint presentation of mine and the complete module of this laws of thermodynamics, kindly email me at ryannicole05@gmail.com. Thank you very much.